I'm going to go through this mechanism first, and then we'll have a little bit of a discussion about it. So this mechanism has us take an aldehyde and react with one equivalent of alcohol. So again, carbonyl-containing compounds like aldehydes, ketones, esters, amides, carboxylic acids, having this carbon doubly bonded to oxygen is a great electrophile. So you need to find your nucleophile, which in this case, the alcohol contains this nucleophilic oxygen atom. Nucleophilic attack moves electrons, generating our tetrahedral intermediate. Let's label that a prime there. As I've highlighted in some of your mechanisms, we want to make sure that we clearly draw lone pairs or bonds of electrons that are on atoms that are participating in our mechanism. And so we want to make sure that we do that. In this case, we really only have a carbonyl-containing functional group that has one other option after this, and that's protonation of that alkoxy oxygen to generate our alcohol, and then deprotonation of our nucleophile to allow us to generate our final product. So we can show this in one step here. So again, we're going to have our protonation of our alcohol there, our deprotonation of what was our incoming alcohol nucleophile, and we generate our final hemiacetal product. I am going to show you the same kind of companion mechanism shown in an acid catalyzed fashion, remembering that carbonyl containing compounds are good electrophiles, but they're not amazing electrophiles. So we can make them more electrophilic if we have a little bit of an acidic condition that allows us to protonate this alkoxy or this carbonyl oxygen, making it a better electrophile. So again, draw our lone pairs in there. Now, it's not going to be a large population of our aldehyde that's protonated, because remember, the pKa for a protonated aldehyde is very, very low. So it's likely to become deprotonated. But all we need is one molecule every once in a while to be protonated so that it becomes a better electrophile, reacting with alcohols, which are not great nucleophiles. And we're going to see a pretty similar mechanism to what we had immediately above it, with the exception that with our tetrahedral intermediate, we don't have a negative charge on that carbonyl oxygen. We will have to think about the fact that our alcohol in our incoming nucleophile was still protonated as it came in. So we will need to deprotonate this and then generate the same hemiacetal final product. So again, a couple of things to comment on here. If we kind of draw some parallels as to what we saw on our previous mechanism, right, just a couple of comments here. This mechanism is nearly identical to what we saw in reaction mechanism 4. So hopefully this was a pretty straightforward one for you to do immediately following reaction 4. Now the R group, that again was the rest of the molecule in a ketone, that was a carbon, we now have a hydrogen since we have an aldehyde. So again, just to kind of draw some parallels, we'll flip back here for a second to the one we had just prior to this. This was a carbon if we have a ketone. This is a hydrogen if we have an aldehyde. And how you can tell what you started with, because one of the things that's going to become important is when we look at something like a hemiacetal or a carbon that contains essentially an ether linkage and an alcohol linkage, is we have to look at whether or not there's two carbons that are attached here, like we had in our ketone, or in this case, this was an aldehyde. And that's going to become important as we kind of start working some of these mechanisms backwards. Again, two alkyl groups being a ketone is what we saw in reaction mechanism 4. This reaction mechanism having a hydrogen gives us an aldehyde as our starting functional group, and so we form a hemiacetal rather than a hemiketal. What's neat and parallel with this mechanism is the biochemical application that we see here is pretty much the same as what we saw with reaction mechanism 4. So I'm not going to go into a lot of detail for that, but the purpose of this kind of chemistry is to allow the cyclization of sugars. And in cyclizing those sugars, what we really do is we protect that reactive aldehyde functional group in this reaction mechanism or the ketone functional group in reaction mechanism 4. And this becomes really important because when we have sugars that are in this hemiacetal form, we refer to them as reducing sugars, since they are actually only one step, a ring opening step away from having a reactive functional group that could undergo redox chemistry. Again, this chemistry that we see in this mechanism, reaction 5, similar to what we commented on reaction mechanism 4, is also a way that we can glycosylate proteins. And glycosylation of proteins is really where we use an OH group that's found in an amino acid residue such as a serine, threonine, or a tyrosine, and we use that as the nucleophile, that as the alcohol functional group, to react with the carbonyl in an aldehyde or a ketone found in a sugar, and then we can, in this way, functionalize proteins. So lots of parallels between reaction mechanism 4 and 5. Mechanistically, it should have been fairly easy to draw. You literally could recopy your mechanism from before, this time swapping out a hydrogen for what was an R group in an alkyl group for a ketone.